There's one thing humans have always been doing, and that is the thing that has been driving our curiosity to discover our world. It's a really simple experiment, and it's one that can not only help us discover what the universe is made out of, but also what the world that is around us is created from. You can see it on the picture, and you can also see it in this demonstration. It's just banging rocks together. The question is, what can it help us discover? If we're trying to think about what the universe is made out of, the basic question we're trying to ask is, what are the main building blocks that create our reality? It turns out that the easiest experiment we can do to discover it is to simply take two objects, clash them together, wait for a time when they break apart, and see what are the smaller building blocks of the atoms. And we've been doing this for thousands and thousands of years. And that, coincidentally, is also what scientists right now are doing in the biggest laboratories in the world. And maybe it's not using rocks. Maybe it's using the tiniest possible elements of matter, like electrons or protons, circling around huge experiments, mostly basic physics experiments. These elements are traveling at 0.9999 of the velocity of light, which is crazy speed, and they're colliding together and creating something which is very similar to what you can see on the picture. The question is, what we discover when we clash them? And this is a question that has been very important to scientists for thousands of years. You might have heard about Democritus. He was an ancient Greek philosopher who thought that the smallest unit of matter we can possibly have is an atom. Atomos means indivisible. It turns out that from his times, we figured out that there are way smaller units inside the atom. You might have heard about protons and neutrons and electrons. It turns out that these too are made of smaller particles, quarks and leptons that glue them together. This is what we call the quantum world. And in the quantum world, the rules are so much different from what we see in our reality. You can look at an object and see, okay, this is a remote control. I can see that it is in my hand. In the quantum world, if you know what you're looking at, you don't know how fast it's moving or what it is. And if you know where it is, you don't know the properties of it, which is the answer to the principle. It turns out that the quantum theory was actually discovered more than 100 years ago now by a couple of old dudes that basically went on an island retreat, sat down in front of a blank piece of paper, and decided to create equations that show how quantum particles are behaving. You can see one behind me on screen. I know it might be a bit scary, but basically it's a partial derivative that tells us that a quantum state, when we derivate it, can give us an energy, and the way in which we describe this energy tells us how the state is behaving. Quantum theory is a very complicated concept because it's a very strange world that escapes our understanding, but I'm trying to bring it to you in a way that hopefully will be intuitive. First, we need to talk about our smartphones. If you look around in your pockets, you might notice that there is this thing that brings the whole world into your reality. It helps you connect with your friends, gather knowledge, do whatever else you decide. The whole world is in your pocket. It turns out that this technology would not have been possible if not for the discoveries that quantum scientists were able to create. Quantum physics helped us create many different elements that shape our reality right now. For example, lasers, or very specific clocks that run our markets, or microchips that are in every single device we use currently. It turns out that a couple of equations that physicists in their labs, in total solitude, were able to create, were able to change our reality forever. And we think this might only be the beginning. This is how we describe a quantum state. You might see that there is a sphere, which we call a Bloch sphere, and on top we have one easily distinguishable state, on the bottom we have another one. You can think of this like an electron that can either have a spin up or a spin down. These are really distinguishable states. It turns out that every single quantum state is not exactly easy to measure. Every state is the superposition to a combination of the 0 and the 1, for example, spin up and spin down. So before you measure a quantum state, you don't know what state it is in, which is a bit crazy. I wanted to demonstrate this with a very nice analogy some of you might have heard of. It's called the Schrödinger stat. poison. We don't know if the animal took that poison or not before we open it. And what might we discover if we open the box? Well, there are two possibilities. Let's open it and see. It might turn out that the animal is completely fine, it hasn't touched the poison at all. Or it might turn out, as we open the box, that it's dead. But before we open it, we have no idea what's happening because we have no outside information that could interfere with the animal. And this is an analogy that can basically show you what a superposition is. Before we open the box, we have absolutely no idea if the animal is alive or dead. Sort of like the quantum state, we have no idea if this electron has a spin up or a spin down. So the cat, or any sort of animal, is in a superposition of two states. Notice that when we open the box, it always collapses. So for example, it can be 30% likelihood that it's dead, 70% likelihood that it's alive before we open it, but after we open it, there are only two results, either good or not. This representation shows you roughly how a superposition might look like. You might notice this point on the log sphere. It's closer to zero. Let's say that zero maps our alive state. So the closer to zero we are, the bigger the probability that the cat is alive. If it turns out that it's dead, the probability is a bit less. Another thing I wanted to show you is basically a misconception that many people have heard about. Quantum can help us send information faster than light, which seems like a bit of bullshit because there is nothing that can be faster than light. So how can it be that we can send information faster? To illustrate this, I wanted to show you a measurement experiment connected with two simple clocks. One of them is left, and the other one is right. We don't know which is which, because we take them away and we close them in boxes. And let's say that one of these boxes is sent to my friend in Australia, another box is sent to my friend in the US. And I want them to perform an experiment where they open the boxes and see which clock they got, either the left or the right. You might notice that if one of my friends receives the box and opens it, and in this case, the glove is definitely the right glove, they can with 100% certainty say that the other glove must for sure be the left one. So notice there was no transfer of information between the US and Australia. It's just that if one glove is the right one, the next one must for 100% be the left. This is what we call entanglement, and it helps us create a quantum state in one galaxy, send it to another galaxy, for example, through quantum tunnelling. We hope this is possible, we'll see if it is. And if we measure one state, we for 100% know what the other one was. Notice it was without the transfer of information. This is one of the crazy things that quantum can allow us to do. So the first glove was the right one, obviously the second one must be the left. And that property is exemplified in quantum states. Now, I want to show you what all of this theory that was developed in lab can actually do and how it can help change our real world. You might notice that behind me, I put a very basic binary representation of something which all of our computers are based on right now. You might have called about bits. You might have heard about bits. There are basically two states that a bit can be in. You can think of it like a wire that electricity is either flowing through or isn't. Let's say that the zero state is no electricity and the one state is electricity. If we have a superconducting system or some other quantum system that serves as this bit, we call it very fancily a qubit. And it turns out that that qubit, just as the animal in the box before we measured it, might actually be in a superposition of two states. And what that creates for us is probabilistic counting. So every single bit, if we take, for example, 10 bits, 20 bits, will create a complexity not of simply 10, but of 2 to the 10, because every bit is two possibilities, either 0 or 1, either alive or dead. 2025 is a very special year. It's the 100-year anniversary of that old guys creating quantum theory. And UNESCO has made this year the International Year of Quantum Science and Technology. We are hoping that after the first quantum revolution, that basically revolutionized the way in which we see our world, for example, through smartphones and fast clocks, there might be a second quantum revolution coming. And it's going to be connected with the qubits I was telling you about initially. You might have seen the picture of a quantum particle on my screen, and you might see the snowflake. They are similar, and not by coincidence. It turns out that if we want to operate on quantum states, everything around them needs to be really, really cold and also kept in isolation from everything else in the world. Quantum states are really fragile. You might have heard about Brownian motion. Brownian motion is a way in which we measure temperature. Basically, the quicker particles are jiggling, the higher the energy and the higher the temperature they have. So if we want to do any measurement or any sort of operation in a quantum state, it needs to be kept stationary. And to do that, we need to lower the temperature and lower all of the noise that the particle might be subjected to. This is why, in order to create any quantum computational machine, we need to be in a humongous lab that helps us isolate the entire quantum computing unit from the rest of the world. And I wanted to take you on a journey on one of these labs. That's IBM Quantum in New York. And I wanted to show you how a quantum operating system would actually look like. So we need to go through the microelectronics engineering lab, which you can see behind me. We need to go through the entirety of all the aperture they have. And actually, in the middle of it, we find a computer that is basically a fridge. This is IBM Quantum System 2, one of the newest quantum systems in the world right now. And you can notice that coincidentally, it looks like a giant family-sized fridge. Inside of it, we have the quantum computing unit, but to get there, we need to go through a vacuum enclosure and something which we call a supercooling fridge that is actually this chandelier. If you've ever heard about a quantum system, you might have seen it basically like in this picture, but what you might not know is the actual computing unit is down there in the middle, and everything else is simply the infrastructure that helps us measure and cool the system down. It's cooled by crazy elements like helium-3 and helium-4. These elements can only be found in nuclear reactors as a byproduct, so it's very hard to get hold of them, but if you do, you can cool the computing unit that's down there to temperatures which are the coldest in the known universe. You might have heard that the vacuum of space is roughly 2 Kelvin, so minus 291 degrees Celsius. It turns out that the quantum computing unit down there is 20 millikelvin. And think for a second, if you are in this room right now, the temperature is roughly 20 degrees Celsius, so roughly 300 Kelvin. If you go outside into freezing cold temperatures, that temperature would be roughly 260 Kelvin. So the temperature decreased by roughly 10%. The decrease in temperature from room temperature to 20 millikelvin, or even from the vacuum of space to 20 millikelvin, is thousands of times bigger. So the way in which we achieve these temperatures is absolutely gobsmacking. What can that help us create? It turns out that these very cool computers are not only cool literally, but also figuratively. Quantum might be the next big thing when it comes to cryptography. It turns out that these very complex quantum states can help calculate different calculations at the same time, in contrast with normal computers that can only do one calculation at one time. And that can help us break the securest ways that we have right now in encrypting data. Which means that if we are not ready for quantum computers when they come, the entirety of the banking system or the internet can be completely put to the ground. This is why I wanted to have quantum as soon as possible. Another thing is complex analysis. If you can do more calculations, you can do them quicker, so you can model problems that were not possible to model before. Another topic, which is actually really cool for some of the people who might be interested in biology and chemistry, is quantum sensing. The easiest way to see how a material behaves, or how a quantum system behaves, is to simply take the quantum system and model it with the quantum system that we're trying to see. This is why if you want to see a nanostructure or any type of chemical compound, the easiest way is to model them with quantum. Drug development is also a very important area. You might know that drugs are basically chemical systems, so we can show them through quantum. That's really cool. And one more, which is actually my favorite topic, very complex graph problems. Any single optimization problem that we have in the world right now can be mapped onto a graph problem. And that graph problem, every single node, can be represented by a quantum state. So if we are able to, for example, streamline the way in which we deliver electricity, or show a way in which we want to put superchargers or electric cars around Poland so that they behave in the most optimal way, this is something that is the best modeled by a quantum computer. On a classical one, it would take days, years, or even eons. On a quantum one, it takes minutes. That's all I have prepared for you. If you don't take anything else stop, please remember, Quantum is not only Finnish Quantum, it's not only a word that sounds cool, but it's actually a new technology that has already changed the way in which we live our world, and we are hoping for even bigger breakthroughs.